Hello, everyone.
Hi,
I'm Prem,
I'm Claire.
and we're the leads for DAV, Digital Design Architecture and Verification Project. So first we'll briefly kind of tell you about what exactly DAV is. So digital design, first and foremost, is the field of electrical engineering that deals in the designing of processors for various devices. So if you've ever used a phone or a computer or even like a graphics card, these are all some of the outputs of the digital design industry. It's a fairly niche electrical engineering field that it's very in demand, but in general, it's not like something that everyone knows how to do right from the get-go, and most people don't really try this stuff out in, say, high school. So it's something that we aim to teach and sort of increase exposure to in DAV.
Yeah, so for our project, we offer two tracks. For DAV Digital Audio Visualizer, students are tasked with hooking up a microphone to their FPGA, which is the chip that we teach students how to build on, to read audio input, and then do some signal processing to it and make a really pretty graph that looks like that. And then our other track, which is the Digital Design Architecture Verification, is for students to create a game, any game that they can think of. We encourage them, and their goal is to have some sort of game controller and communicate with it using their FPGA to have some user input for their game. Yeah.
And without further ado, we'll now give it up for our students that have been working on these projects throughout the year.
Hi, my name is William. Unfortunately, my teammate Kevin had to leave because he has class right now. But I'm just going to give a very high-level overview of what kind of goes into a digital audio visualizer. So on the left, the first thing we have is a microphone because we need some way to pick up audio signals, right? But then from there, we need to hook up the audio samples to an analog digital converter because we want to work in digital realm because we can't actually perform analysis on purely analog signals. Once we have that converted, we have an FFT module, which is a digital signal processing module that basically converts the audio input to like the frequency domain because we first have it into the microphone as in the time domain. So there, once we have the frequencies, we can actually perform the actual graphical display that we want to see. First, we pass on the frequencies to a graphics controller, which basically determines pixel, but like what color each pixel is going to be. It retrieves, the graphics controller retrieves the pixel information from the VGA driver so it knows actually what pixel it's trying to determine the color for. Then we have, for each pixel, the color of that pixel defined in RAM. The reason why we don't just pass on the color input to the VGA driver is because by default, our display draws the image pixel by pixel, but doesn't draw the image frame by frame, which means if you don't have the RAM file, we're gonna have something like screen tearing and other issues like that. Once we have all the colors defined for each pixel, we pass it to the VGA driver, which actually manually draws the colors for each pixel. And then the end result is a functional digital audio visualizer, as shown on the right, that displays the frequencies for the audio sounds. And now I'll pass it on to Kate, who actually go more in depth on the signal processing.
I'm Kaden, and yeah, basically once we get that initial digital audio visualizer, it gives us a really nice platform to try out a lot of these signal processing techniques that we might have learned in our classes. So the first of these is the Hamming window. Essentially, when we do that FFT, that frequency transform, we're only doing it on a tiny, maybe 32 sample chunk coming in from our microphone, and that might give us really weird edge effects. Now, these edge effects cause something called spectral leakage. Basically, this signal up here, it should, in the frequency domain, just be like a nice clean spike, but what are all these blue things? That's basically the remnants of these edge effects coming in. And how we might be able to get around that is we can say, well, if we take our signal and we multiply it by some tapering window, that'll kind of smooth out those edges. Then when we throw it into the frequency domain, even though we might not have kind of the same I guess kind of we have the trade-off of sure our sharp peaks might get a little wider, but all of those leakage effects, those ripples, we've kind of smoothed them out. Then another one is digital filtering. This is one of those core operations you learn starting from your very first class about signals. And it's crazy that it's really hard when you do it in class, but trying to implement it on something like an FPGA, it's actually pretty easy. We just take, say, the last 5 inputs of our microphone, we'll multiply them some value, and then we'll just add them up. That's all it takes to implement a digital convolution operation, which lets us do cool things like get rid of background noise, extract voice details, all these kind of bonus features. And that's it for me. I'll hand it off.
I'm sorry, could I ask a clarification question before?
Yeah.
As an introduction, we have a group of maybe like 15 high school kids here who are like really into engineering, science, etc. But obviously haven't taken, they've taken some electrical stuff, right? And as an aside, they're all skipping school right now to be here because they wanted to check this out. Could you briefly, if we step back, talk about what an FPGA is? You mentioned FFT. You talked about going from time domain to frequency domain. Like, what is that? Why should we care? What's going on?
Sure.
I apologize to everyone else here who knows this,
No,
but perhaps a real
totally
high level DSP-ish type of thing.
Yeah, so I'll talk about what an FPGA is, and then I can give it to Caden to talk about like the more signal processing stuff. But basically, so I mentioned earlier the digital design is the sort of electrical engineering field that goes into how do we make chips for phones, computers, graphics cards, etc. So basically an FPGA is a development board on which we can actually prototype some of these. So like you have, if you've ever used like an Arduino or something and you've made like a really basic program that does some sort of like robotic style task or controls LEDs or whatever. Think of an FPGA as like similar to an Arduino, but you can build these digital circuits and basically prototype what might eventually become some sort of fancy computer processor. And that's pretty much what it is.
What does FPGA stand for?
It stands for Field Programmable Gate Array, but those words probably mean very little.
Can I challenge you to explain what each of those
Sure.
broadly?
So, I mean, it's an array of logic gates, like ands, ors, nots, etc. Basically a bunch of smaller logic blocks that can be put together in various ways to form these digital circuits. And the reason it's called field programmable is because, well, it's a board on which you can prototype various types of circuits, so you can quite literally program it in the field. When you're like on the fly while you're trying to build these circuits, you can program it with different things and test them. And it's field programmable gate array.
Thank you.
Of course.
But yeah, and to go into the FFT, first, yeah, FPGAs, it's a microcontroller, but really annoying. But the trade-off of getting to do something super specialized, which is often really good for some of these signal processing operations. Signal in this case is the audio kind of going into a microphone. And when we say we're taking the FFT or converting to frequency domain, I have a picture right here. This is basically decomposing our signal into these representative kind of sine waves. A sine wave just being kind of a very neat up and down squiggle. These can be faster squiggling, slower squiggling. That's what you might hear normally as like pitch, like, oh, they have a deep pitch or a high pitch. We can represent, say, this signal up here, what would the equivalent set of squiggly sine waves be that we need to represent it? And each of these is the frequency, that pitch of the sine wave. So it's just a different way to understand a signal, to go from something that we're looking at in time that might be complicated to, oh, it's just a few of these waves added together at different frequencies. And from there, that's where we can get into all of these more complex effects. And we can definitely go into that more with our tabling as well. So we will have a demo showing all of that.
And so FFT stands for?
FFT, it stands for, way back, the fast Fourier transform Fourier transform is just that general procedure to go from time to frequency, or from our real signal to all the squiggles that make it up. Fast Fourier transform, it's kind of just an algorithm to do that switch very efficiently in computation. It's pretty complicated, which is why it's kind of a big piece of our project to try and implement it.
Cool. Thank you.
All right. Take it up.
We're going up. I think you're holding it upside down.
Alright, thank you. So I'm Oliver.
I'm Justice.
I'm JC. Sorry. And then we're here to present our topic on the instrument classifier using the FPGA. So I'm pretty glad that Caden talked a little bit about pitch and its relation here, because as it turns out, all sorts of instruments such as saxophones or trumpets sound different to us. But why do they actually sound different? And a lot of that comes down to something called timbre, which is essentially just this unique mix of frequencies that each instrument provides. We can see here that they have like different patterns that we can plot out. And so we thought, well, given that we're doing the FFT in this project and it will tell us more about frequencies, surely we can use some kind of like classifier with the FFT. Which is exactly what's going on here. We got some data and we have some classifier options here. We originally wanted to do some fancy machine learning with like a neural network. That's really hard. So I think we ended up just going with the one nearest neighbor. So I'll hand it off to Justin.
Yeah. So how is our classifier going to work? So first of all, we need to take our microphone input from our environment. So we plug a microphone into our FPGA board, and so we can take samples from, like audio samples from the outside world at 4.4 kilohertz. So that's 4,400 times a second, and then we have to go into the signal processing step, which includes the fast Fourier transform that Caden talked about earlier. And so that requires us to do a lot of calculations. So we have to do that slightly faster. So this 440 kilohertz sort of speed is what we're striving to sort of do all of these calculations at. And so it's got to be a little bit faster than our sampling rate. So that requires one big controller unit to sort of handle these two speeds with two different things called clock signals. Those are what drive our digital circuits and keep them synchronized with each other. So and on top of that, that controller also needs to handle basically displaying our output, whether it's on these like 7-segment LED displays or more complicated protocol called VGA, which is basically displaying video on an external display. And so for all of this, we need to program a controller unit and sort of debug it. And the way we're going to do that is using a digital logic simulator, which is where JC is in.
Oh yeah, so for our project, we needed to make a 1024 point FFT, which is far beyond the size that staff teaches us. And the reason for this is because then the bin width is about 4 hertz, which we experimentally determined is good enough for capturing the peak. And so because of this, we had to shift away from the more intuitive recursive FFT design into an iterative version. And by doing that, we were able to shrink the number of logic elements required to actually implement the system from over 200,000 to just 900. So it actually fits on the device. And then part of doing that included using for dual port RAM to actually store values, and there's a not very complicated, but an existing handshake protocol to actually read values in and out of it. And as Justin mentioned before, there were 2 clock speeds. So when we actually sampled the mic, we use a slower speed, but then in the actual calculation, it takes about 50,000 clock cycles, we have to use a much faster clock speed. And then, so by doing this, you can use combinational logic because it's easier to code and extract the harmonics, and then we fit it on 5 classes. These may or may not have been cherry picked, and out of these 5, we were able to get 45% accuracy, which is statistically significant. But, yeah, that's pretty much it.
Any questions?
Alright, so enough of audio, right? So our team decided to make a video game. So unfortunately Brian's sick, he cannot be here, but I'll continue with that. So we decided to make Pac-Man on the FPGA. And from a high level overview, we basically processed an input from some kind of game controller. We decided to use the Donkey Kong bongos. We also ended up using the NES controller as well. And we have to read the bits from the controllers, process what they mean, translate that into some kind of player movement, whether it's like up, down, left, right. And then the game logic has to take into account what the player is going to do, and then that changes the output, which in this case is a VGA display. And to do this, we use a lot of FSMs, which stand for finite state machines. Basically, anything that has a state, we can use this to model that. So all the different ghosts have different states, Pac-Man has different states, and the game itself has different states. So, yeah. So one of the challenges we faced was to process the input from the game controller itself. The bongos needed a very specific timing to communicate with it. Basically, we send it a 24-bit command message and a response with a 64-bit response of the state of the buttons. And figuring out the timing and communicating with the bongos was definitely a challenge. So we used the logic analyzer to read the actual like highs and lows of the signal. And this is a little bit some screenshots of the logic analyzers. Some other challenges we faced, but I don't have quite enough time to talk about here, including just putting everything, the timing, optimizations made to the graphics controllers to like fit the entire maze in the RAM. That was definitely a challenge. And also handling all the states of all the different sprites and all the moving parts was a challenge as well as the interactions between like the Ghost and Pac-Man, for example. And finally, we get something like this. Fun fact, each ghost has a different personality. And so each ghost like chases Pac-Man in a different way. So we also implemented that. The red ghost basically follows Pac-Man. The pink one tries to target the square like 4 spaces in front of Pac-Man. The blue one takes into account both the red ghost and Pac-Man's location and tries to like ambush Pac-Man. And then finally, the orange one, if it's far away, over 8 tiles away, it moves towards Pac-Man, but once it gets too close, it's kind of shy, just like turns around. But yeah, that's the gist of it. If you come by to the table, you can actually play Pac-Man, so please stop by.
Were the personality differences, those are your, is that in the actual game or is that your?
That's in the actual game, yeah, so
Oh, I didn't know that.
we read up on that and like actually implemented all that.
Oh, okay, all right, cool.